Hi and welcome to this IB Maths Intense session number 7 on sequences and series, this time looking at the financial applications of these techniques and more kind of real life practical problems using the concepts we've learned earlier. This is syllabus part SL 1.4, so it's something for everybody, and if you look in the syllabus guide, there it is, SL 1.4, financial applications of geometric sequences and series, particularly looking at things like compound interest and annual depreciation, which all work in a very similar way. So in this video, let's take a look at some of the types of questions we might get asked. So first of all, just using the idea of simple interest, this is the sort of interest that links to what we did on arithmetic sequences. So in the example that's given here, a bank agrees to give me 3% simple interest per year for each year that I leave my £1,000 investment in the bank. Now here, this just means I get the same 3% interest on my original investment. Well, hopefully you can calculate that. 3% of my 1,000 is the total of £30 per year. And that doesn't vary, even if the amount in the bank increases because I've got interest in there. I'm not getting interest on interest. So it's not compound interest, it's not a geometric sequence. I'm just getting every year £30. So at the end of year 1, I'll have my 1,000 plus 30. And at the end of year 2, I'll have my 1,000 plus 30 plus 30, and so on. So you'll see that by the end of year n, I'll have 1,000 plus, well, n lots of 30. So this is very similar to un equals a plus n minus 1d. The only difference here is that n here we're taking into account all the years, because effectively the amount at the end of the year is like the beginning of the next year. So we're not subtracting 1 from the number of years here. So if I wanted to calculate how much after 10 years, after 10 full years, this is effectively the amount that I'd have at the beginning of the 11th year. So my UN here would be, effectively it's U11, isn't it? Is my starting amount 1,000 plus 10 lots of the difference, which is 30 each year. So I'm getting 1,300 altogether at the end of that time. Just be careful with what you use as your value of n here, because it can be a bit confusing, because a year has a beginning and an end, and we're interested in this case, the end of year 10 is effectively the beginning of year 11, so I have to set n to equal 11. That's simple interest, just getting the same amount every year. But it may be that the bank agrees to give me compound interest. This is 2% compound interest per year for each year that I leave my £1,000 investment in the bank. And in this case, I'm getting a benefit from the money that I leave in the bank. I get interest on my interest. It's like a geometric sequence. So effectively, here I've got my UN equals a Rn minus 1. So if I use that geometric formula, I could say the amount I have in the bank at, well, let's go with the same thing. I'm going to go with U11 again here. At the beginning of the 11th year would be my starting amount, 1,000. And then my rate of interest, 1.02, is the same as compound interest of 2%, is the same as a common ratio of 1.02. And I'm going to multiply, I'm going to make that to the power of 10, because I'll have 10 complete years worth of interest. So effectively it's U11 that I'm interested in here, the amount at the beginning of the 11th year, and that would give me the total of 1,219 in the bank with 2% compound interest. It's a geometric this time because I'm getting interest on interest. You might get a comparative question. So I deposit £2,000 in the bank. They offer me 2.5% simple interest or 2% compound interest for each year I leave my investment in the bank. How many full years would I need to leave my money in the bank for the compound interest option to be better than the simple interest option? Well, there's a couple of ways to do this. I'm going to show you using not using a graphical calculator as such. Let's use a trial and improvement type method here. But we're interested in the situation where my 1000 times 1.02, which is my 2% compound interest to the power of n, that's the amount that I've got in the bank as a result of compound interest, exceeds the 1000 plus 25n, the 2.5%, which is £25 difference that I get every year. So I could do this just trial and error with the calculator and just dip in, let's try 10 years. And we could say on the left hand side is with compound interest. 1000 times 1.02 to the 10 gives me 1218.99. And on the other side, I'd have 1000 plus 10 lots of £25 gives me 1250. So after 10 years, it's still better to leave the money with the simple interest, which is over here, compound interest over here. Let's try 20 years then. 1000 times 1.02 to the 20 gives me 1485.95. And if I go with simple interest, this time we've got 20 lots of 25. And it's still better to stick with the simple interest option. I've got 1500 there. But we're getting close. So let's try 25 years. 1.02 to the 25. And that's 1640. And on the other side with simple interest, 25 lots of 25. Now, is it now better? Yes, it is. 1625. So it's now become better after 25 years. But maybe it got better earlier than that. So let's work backwards. True trial improvement, 25 years. Let's try 23 years. We're getting close to an answer here. 1 times 0.2. 1.02 to 23 is 1576.90, and over here it would be 1000 plus 23 lots of 25, which equals 1575. That's very close, but this one is our correct answer because, as you can see, it just crosses over at the end of the 23rd year. It's just better with compound interest. So 23 years. Now, of course, that was a very unwieldy way of doing it using good old trial and improvement methods. Of course, you could take this particular equation here, or inequality, make it into an expression. Here it is. And what we're looking for is where this particular expression, 1000 times 1.02 to the n, minus what's on the right side, equals 0. Point of intersection will tell us where there's a crossover. And as you can see here, I've graphed that. Of course, equals 0 when n equals 0. That's not interesting for us. But then it comes back here, over here. And sure enough, you'll see that that is just before the 23rd year. So during the 22nd year is when it crosses over. So you can see here, x equals 23 would be the best, or the time where compound interest becomes the better option. So you can plot that using your graphical calculator. Working backwards question. Started my job 1995, received a pay rise of 2.5% each year of my previous year's salary. By 2019, my salary was $72,350. What was my starting salary? So this is just about working backwards. A is my starting salary, and then I've had, well, between 95 and 2019, 24 pay rises. So 1.025 is a 2.5% interest to the power of 24, because it happened 24 times, equals 72,350. And then this is just about working backwards. So A must be equal to 72,350 divided by 1.025 to the 24. And if you work that out on your calculator, you'll see it comes to the nice round figure of 40,000 was my starting salary. Now, let's finish with a really tough question. Need to pause this if you want to read the question so that you really get your head around it, but I wanted to show you something that was a little bit more difficult. So, I borrowed £15,000 to buy myself a car. I have to pay the loan back in monthly instalments. Interest is calculated monthly, but is charged 12% per annum. How much money do I need to pay each month if I pay back the loan in exactly 5 years? And just for clarity, I pay each month after the monthly interest has been added. And there's a lot of information in there and it sounds very complicated. So a few highlights to do. So I borrow 15,000, that's how much I'm borrowing. It's monthly interest, but it's charged at 12% per annum. So the way that that works is 12% per annum per year equates to 1% per month. It's as simple as that. If it was compounded on a monthly basis, then obviously it would be different. But here, the 12% has been divided into 12 equal chunks of 1%. How much do I need to pay if I want to pay off the loan in exactly 5 years? So 5 years is interesting here. And also, I pay each month after the interest has been added. So let's model here exactly what this looks like. How much do I owe at the end of month 1? Well, I've got 15,000 and I'm paying interest of 1.01%, and then let's call this A for the amount that I pay, and then I subtract the amount that I'm going to pay, which I don't know what that is yet. At the end of month 2, I'm going to have the amount that I had at the beginning of month 2, which is the total above, 15,000 times 1.01 minus A. I'll put that in brackets. And then I'm going to multiply that by 1.01 because I'm paying interest on what was left at the end of month 1. And I'm going to subtract A again. And then at the end of month 3, I'm going to have what I had at the end of month 2. I'm just going to copy that out from above, minus A, times 1.01 minus A, and then I'm going to take all of that, and I'm going to multiply that by 1.01 and subtract A. These are just, it's a running total, but what would be good is if we simplify that, we can hopefully see a pattern. What we can see is, if we expanded all of that out, we'd have 15,000, this bit, times 1.01 once, twice, 3 times. So times 1.01 to the power of 3. And then minus, we've got A times 1.01 times 1.01 twice. And then we've got this A multiplied by 1.01. And then we've got A. Now hopefully you can see that this little bit here is a geometric sequence with 3 terms where U3 equals the starting amount A times R to the n minus 1, or A squared in fact. So that's something we recognize. So if we know that, we know then that the end of the 60th month, let's see if we can generalize. This would be 15,000 times 1.01 to the power of 60, because at the end of 3 months we still owed to the power of 3 there, and then it would be minus, and it would be this geometric with A 1.01 to the power of, it'd be to the power of 59, because it's n minus 1, minus A 1.01 to the 58, and that would go all the way down till it was subtracting A at the end. Now, it's complicated. We expect to owe nothing at the end of all this time, so at the end of M60, month 60, we expect that little calculation to give us an answer of 0. Let's do something genius now. So this is 15,000 times 1.01 to the 60. But this, we have the formula for the sum of a geometric sequence with the first term of A and a common ratio of 1.01. it is, if we remember, sum of n is un r to the n minus 1 over r minus 1. So, sorry, that would be not u to the n. Let's just get that right for you. Silly mistake. That should have been u1, not un, u1, the first term. So our first term here is a, because we're looking at it in reverse, and then r to the n, 1.01 to the 60 minus 1, all over 1.01 minus 1, which is 0.01. Now, if we rearrange that, and we need to set that to 0, of course, because we want to owe nothing at the end. Then we get a is equal to, do this calculation yourself, I don't want to take up too much time, but if we multiply everything by 0.01 here, and then rearrange for a, we get a is equal to 27250.45048 all over 81.66966,986. I'm being as precise as possible, which is equal to £333.67 per month. Now, that looks a horrendous amount, doesn't it? 333.67 per month. And if you multiply that by 60, just for interest, you'll see that means the car cost, total cost, was £20,020.20. So quite a lot more than the original £15,000 price. That's complicated. Look through that yourself slowly, just to look at what I've done there. But the secret to that question was writing down what's happening in the first few years to see if you can spot the pattern, and out of that came a geometric, which we can find the sum of, and then a nice simple expression on the left hand side, which was just for the nth term of a geometric sequence. Whew, that was tough, but bear with it, try those questions yourself. You've got the techniques that you've learnt through geometric and arithmetic sequences and series to cope with that. You just need to think carefully about what the question's asking you and what assumptions you're going to make. But I hope that was useful. Thank you for watching. Don't forget to like the video, subscribe to the YouTube channel IB Maths Intense, tell your friends I'm here, and drop me an email at ibmathsintense@gmail.com if you've got any queries, if you've got any requests, any mistakes that you think I've made there. I'll be very happy to hear from you. But in the meantime, you take care and enjoy your maths.